Hey, hello. Welcome to my electricity guide. This should cover direct current, chapters 12 and 13 from AQA for the A level. It should be a full guide for those chapters, and the approach may be different to what you've seen before. It's a slightly different way of thinking about electricity, but hopefully if you follow through the guide, you should find electricity is a lot more understandable and less intimidating. So if we just make a start here, all the simple stuff to begin with. So what we're going to be using heavily throughout this guide is an analogy, a set of analogies for electricity. So what we're going to be saying is that electricity is essentially like water flowing in pipes. So if we have a pipe and a bunch of water flowing down it, well then the amount of water is going to be the current. And since electricity is made up of electrons, what we're going to say is that the amount of water is equivalent to the amount of electrons flowing down the pipe. So that's the first definition and analogy to be aware of, which is just that current is the flow of charge per unit time. But what I'm going to be saying is that you should think of charge as the number of electrons and current as how many electrons are flowing per unit time. So if you stick to this analogy of water flowing in pipes, then the first thing that makes us think of is, well, how then do we measure current? Well, if you want to measure the amount of water flowing, all you have to do is sort of ask at a single point how much water is flowing past. So you're just going to put something straight in line, e.g. in series with the circuit you already have. And so an ammeter you'll always see in series with the rest of the circuit. So for example, if we just sketch a simple circuit here with a resistor and a battery, then you'll usually see the ammeter like that, just in series. So we would not want to put it in parallel like this, for example, because effectively that's not measuring the amount of water flowing around the circuit. That's actually just providing a new path for water to flow down. So we don't want this. And then you sort of immediately from understanding that, you ask yourself, well, what properties do we want an ammeter to have in order to be able to do this? Well, we want to measure the amount of water flowing around this circuit, and we don't want to change the circuit when we add this ammeter. So in other words, what we want is all ammeters to have zero resistance, because that way, when we put an ammeter in, it doesn't change the circuit that we're measuring. If you don't have any resistance, it's not going to affect the circuit. So that's the first use of the analogy. The next thing that this analogy explains is the fact that because it's like flow of water in pipes, any junction where current can split, for example, in this diagram below, we can see that, well, if you imagine a bunch of water flowing in here, a total amount I, well, then it has two choices when it gets to that junction. It can either go down this path here or this path here. And so it's going to split, and you won't get any buildup of water anywhere. You can't have sort of water building up in a river or in a pipe. And so what we can say for sure is that the amount of current flowing into a junction must be the same as the amount of current flowing out, which immediately gives us this equation, and also explains why current splits when you've got a parallel setup like this, where there's two choices for it to flow down, and also why if I have a circuit like this, where there's only one path for current flow down, regardless of how many different components we put in it. Let's just put something like this. And I want to know what's the current here, 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 or here. Well, the current's going to be the same at every single point because it's just the amount of water flowing, and there's only one path for it to flow down. So that's an introduction to the idea of current. Resistance, the actual definition you want to use for definition questions is simply that R equals V over I. e.g. the resistance across a component is the voltage across it per unit current. Now, that's the definition you want for definition questions, but it's not particularly illuminating in terms of how we should think of it. So the second part of the analogy for resistance is that you should think of resistance as being sort of how thick your pipes are, how easy or difficult it is for water to get through. So for example, high resistance pipe, well, from the sounds of it, it should be very difficult for water to get through. So we can basically think of that as a very thin pipe. Whereas if we have a low resistance pipe, then it should be very easy for water to get through. And this analogy also helps to explain what effects increasing resistance has, or adding new parts in parallel or components in series, etc. So just using this analogy, everything should become very intuitive. For example, if I have a circuit like this with a resistor of resistance R, like that, then at the moment we have a pipe of a certain thickness. Now, if I choose to add another component in series like that, what have I done? I've added more resistance. In other words, I've made the pipe thinner. So current will fall. That should make sense. It's pretty obvious. But if I do this, so I've got my original circuit like this, and I choose to add a resistor like this, well, I haven't actually changed the original path at all. All I've done is added a new path. And what will happen if I have a pipe and I leave that alone, but add another path for water to go down? Well, it means that it's easier for water to flow. And so total resistance must fall, which explains sort of intuitively why, if you ever add a component in parallel, you will always decrease the total resistance of the circuit. Now, we'll look at that in more detail, but it's just useful to have a general idea of why it is when you add these components in parallel that resistance tends to fall. Then resistivity, just quickly, is a property of a material that just determines how much resistance it has based on its dimensions. So if you imagine you have a wire made of some material of resistivity rho, then the resistance, if we call this, let's say it's got a cross-sectional area, which is obviously to do with its thickness of A, and a length of L, then its resistance will be the resistivity times the length over the area. Now, just think about that intuitively. It should actually make a lot of sense, because as a pipe gets longer, you'd expect it to be more difficult for water to flow through. So as we increase L, resistance goes up. But as a pipe gets wider, e.g. we increase the area, then it's easier for water to flow through. So the resistance goes down. So resistivity, usually the questions on this are quite easy, but again, just intuitively, it should make sense. Now, it's worth just talking about how you should think of current, resistance, and voltage, which we'll get onto in a second. Just remember that resistance is an intrinsic property of something. So if I have a resistor of 10,000 ohms, then that is the resistance of that resistor. It's not, while the resistance of something can change if you change the temperature, it's much more useful to think of resistance as just an intrinsic property, sort of like mass or volume, as in if a 10,000 kilo ohm resistor has that resistance, then it doesn't matter what circuit it's put in, it has that resistance. And the voltage and current are more sort of context dependent. So we'll talk about that in a second. But just remember that resistance of a certain component, in the absence of any other changes, will be just constant. And then just a quick note, just for these sort of, small, easy one-mark questions that you need to know the definitions for. A superconductor is a material at which the resistance falls to zero below a certain temperature, which allows very large currents to flow without any power losses due to heat, which we'll talk about more later. but just remember that superconductor is just effectively, it has zero resistance, but only below a certain temperature. So you usually need to cool them to extremely low temperatures of sort of minus 200-ish degrees C to actually achieve this. But obviously very helpful, because as you will know, if you have a resistance and you flow current through it, then it tends to heat up. That's obviously wasteful in terms of power, but also if you're trying to flow a lot of current through, then most things will start to melt if they get extremely hot. So we want to use superconductors. Okay, now on to voltage, which is easily the most difficult concept for most people. And this is probably where this guide will start introducing things in a slightly different way to what you may have seen before. All I would say is keep an open mind and just see whether this web method makes doing questions much easier and more clear. I think you should find it's helpful. So the first thing is just that the definition you want to use for definition questions, very much not particularly useful in terms of any practical understanding, but you need to know the definition, is the voltage is E over Q. In other words, where E stands for energy. So we've got, it's the work done or energy supplied per unit charge. So that's the definition you want to know, but it's not what we're going to be using practically, because it's not necessarily that illuminating. So what we're going to be working with that may be new is that the voltage, otherwise known as potential difference, is the difference in energy of a single electron measured at 2 points. Now, this may be new to you, but what I'm going to show what I mean by that, if we have a resistor here in a very simple circuit, and we say that the battery has 12 volts of energy, and by the way, this section is extremely important, so make sure you understand this part, and it will make a lot of electricity questions very simple and easy to understand. So what does a 12-volt battery do? Well, it effectively sort of forces electrons around the circuit, and it gives each of them, when they start, it gives them 12 units of energy to spend. And what you can say in the circuit questions is that electrons always, 100% of the time, no matter what circuit you're dealing with, have to spend all of their energy by the time they get back. So if we've got current going around that way, then we know that all the electrons start with 12 units of energy and finish with 0. And then if you follow, as soon as you label this on, if you follow the electrons round, you know that they have to spend their energy. And in this very simple circuit, we know that there's only one place that they're allowed to spend it, which is across the resistor. So by the time the electron gets to here, it hasn't had a chance to spend any of its energy yet, because it hasn't encountered any components. So it's still at 12 units of energy. And if we sort of track the electron back to here, sort of thinking about it that way, well, we know it has to be at 0 units of energy here, because if it wasn't, it's going to finish off the lap still with units of energy, which we know it's not allowed to do. And so that we can draw on very easily. And therefore, what we can say, using this definition, that the voltage PD across a component is the difference in energy of a single electron measured at 2 points. What I mean is that if we were to connect a voltmeter across here, well, we know that that voltmeter is going to read 12. And that tells us that the electron has spent 12 units of energy across that component, across that resistor. So the voltage of this guy will be 12. Now, obviously very simple at the moment. Just bear with me and you'll see how useful this approach becomes. So for using this approach, what you want to bear in mind is a few things. So every electron takes exactly one path around the circuit, and it just always uses up all of its energy, and always starts with the energy given to it by the battery. So that's one thing to keep in mind for this approach. The other thing that will become important on more difficult questions is that at a single specific chosen point in the circuit, all electrons have the same amount of energy remaining. You cannot have two different energies at the same point. Now this becomes, it's less intuitively obvious, but it's a very easy rule to apply. So for example, if I am told that I have a circuit like this, it's got a 12-volt battery, and we've got some black box of components. I don't know what's in there. And we've also got another weird box of components here. Right. And I'm told that what can we label on? We know that we've got 12 units of energy here and 0 units of energy here. And we also know, therefore, by the time an electron gets here, well, it's still got 12. And by the time it gets here, it's got 0 because it's got nothing, nowhere else to spend. And so we know for sure that electrons, they can only choose one path around the circuit. So at this point, an electron can either choose to go this way or it can choose to go this way. Now, what can we say for sure? Well, regardless of which path it chooses, we know that by the time it gets to here, it has to have 0 units of energy left. So without knowing anything about these components, I don't need to know anything further to be able to say that, well, we've definitely had to spend 12 volts of energy across this guy, and we've also had to spend 12 volts of energy across this guy, because how else are you going to get from 12 to 0 on an electron that's followed either one of the paths? And so you can see very quickly that this analogy should be hopefully making things clear on why, for example, electron voltage doesn't split in parallel setups, as in we've got a 12-volt battery, we've connected 2 components in parallel, and just looking at this, they've both still got 12 volts. So that should be explaining that. And similarly, if I have a setup like this, and we'll talk much more in detail about this in the bits coming up, but just at the moment, it should be sort of making things clear in your mind what's going on and making things more intuitively understandable. We know we have 12 units of energy here. We know we have 0. Let's say that these are the same resistance for now. Well, by the time an electron gets to here, it's got 12. When it gets here, it's got 0. And for these components, because they're the same, they're going to use the same amount of energy. But we'll talk. I don't want you to worry about that too much now. We'll talk about that more later. But effectively, you can see that, well, the electron has to spend, we know that it's spending 12 units of energy across both of them. And so intuitively, it should make sense that it's going to share it. And because they're the same, this guy's going to get 6 volts and this guy's going to get 6 volts. And we can do more with this. We can go further and we can say, well, we also know, therefore, that this guy, how much energy does it have left at this point? Well, there's 6 left. And so let's say I made this circuit a bit more complex and added some component here. And here. And let's say that this guy was R. Let's say this guy was 2R and this guy was 2R. And then they connected a voltmeter across here. Well, this is already the kind of question that starts to confuse people quite a bit in terms of solving it. But with this approach, you should see that it's very easy, because we know that the electron at this point had 12 units of energy, and then it chose to go down either that path or that path. So we've done the top path, that's fine. And so doing the bottom path, well, we know it's still got 12 units of energy left because it hasn't spent any yet. And we know it's got 0 when it gets to here, because it's not got a chance to spend any before it finishes. And these components are the same, so it must spend 6 across this guy and 6 across this guy. I mean, it's got 6 left here. And at this point, this question's solved, because what does a voltmeter do? Well, it measures the difference in energy of a single electron measured at 2 points. So the energy of the electron here is 6 at the top and 6 at the bottom. So what's the voltmeter going to say? Well, it's going to say the difference, which is 0. That's the reading on the voltmeter there. So hopefully this is already starting to show the utility of this method for approaching questions. The other thing that's useful about this approach is we know that voltage is defined as the difference in energy of an electron at 2 points. So if I ask the question, what is the voltage at the point A? That doesn't make any sense. As in, that's like asking the question, what is the distance between point A? It doesn't make sense question because it's defined as the difference between 2 points. And so you are always going to be measuring voltage as a difference between point A and point B, which is why you would never connect a voltmeter in series in a circuit. So what you will never see, except in very special cases where you're trying to measure something called the EMF of the battery, which we'll talk about later, but you will not see this setup. for lots of reasons, but the most obvious reason is that it doesn't really make sense. Like we're trying to measure the difference at 2 points. And so we just tried to put it in the circuit and it doesn't really know what to do. So we don't want to see this. And instead, it should immediately make sense that we'd connect a voltmeter like this, be across a component in parallel, so that we're clearly measuring between 2 points, this point and this point. And then once we've done that asks the question, well, what sort of properties do we want a voltmeter to have? Well, there's a very practical answer. Once we've added it to a circuit, we're trying to measure this circuit without changing it through the addition of a voltmeter, because if you change the properties of the circuit when you add a voltmeter, it sort of defeats the point. And so what is adding a voltmeter in parallel? Well, this is usually with most components, this would be a new path for electrons to flow down. And we don't want that because that will change the circuit. So we want new path to be impossible for electrons to flow down. In other words, infinite resistance. Because if we've got an infinite resistance, it's like a pipe that's infinitely thin, and so no electrons will flow down it, and that way it won't change the circuit. So in other words, voltmeters, so that current doesn't flow through them, we want voltmeters to have infinite resistance and be connected in parallel. So hopefully that makes sense, and you can see we're already starting to address sort of common questions that you might get, and obviously things will ramp up as we go through. So I've been sort of flippantly talking about in series and in parallel. Most people sort of have a vague idea of what this means, but I just want to discuss it a little bit here, just to make sure you're very clear on what series or parallel means. Now, what we're going to be doing in this chapter is considering electrons traveling around circuits, sort of following their paths. And that makes considering the idea of series or parallel very simple, because in series simply means that an electron has to travel through both components in order to complete its lap. Whereas in parallel means that the electron has to choose one of the components in order to complete its lap. So for example, what you can see below, actually, I've already got a diagram here, so let's just use this. I've got the actual path of the electrons going. Obviously, current flows the opposite way, which is very annoying. Usually we'll be talking about the direction of current flowing. It doesn't actually make a difference, but let's actually talk about the actual path of electrons here. So an electron can start off here, go around, that's fine, and then it gets to here. And in order to complete its lap, it can't go through all of these components. It has to make a choice. So in other words, it splits off here and here. So, but if it chooses the top lap, then it has to go through A and B. So we know that A, B are in series, whereas it could have alternatively chosen to go down through C. So C must be in parallel with A and B. And then once you've done that, you've sort of met up here, and then you can say that D and E must be in parallel, because again, it makes a choice. They're in parallel with one another, but you could argue they're in D and E, the combination D and E are in series with this little block, right? So you've got sort of two blocks in series, if that makes sense. Don't worry about it too much there, but just that should sort of clear up any misunderstandings on series or parallel. Now, one important thing, you don't get this too much in A levels, but just be aware that if you get given a circuit that looks weird, for example, let's say it looks something like this. This can be very confusing to try and do calculations on, but the actual geometry of the circuit doesn't matter. All that matters is that you keep everything in the same form in series and parallel. So if we just redraw this, we can say that, okay, well, what choice do we have? Well, when we come out of the battery, we've only got one choice. We have to go down that way and go through him. So we can, when we're redrawing just carefully, we can say, okay, for sure, I know that we've only got one choice. Then what happens? Well, after we've gone through him, we get to a junction with a choice of two paths to go down. You know, that way or that way. So on my new diagram, I'm just going to split into two. And one of these paths only has one resistor on, and the other path looks like it has two resistors on in series. And then those paths, sort of just following them around, they join back up here. So we sort of can be fairly confident we've represented it nicely. And then we're at this point and we can just go back to the battery. And so we've redrawn the same circuit, but now hopefully it looks a lot simpler. We know how to deal with that kind of circuit. So just be aware, if they draw things weirdly, or if they draw, one thing they do often do is something like this. That's just a way of confusing you. There's no difference to this being like this. So just be aware that the only thing that actually matters is whether they're in series or parallel. And if the circuit itself looks confusing because of the way it's drawn, feel free to redraw it because it can make things a lot easier. Okay. Now, just very quickly, I'm sure you'll be aware of all this, but I'm going to talk a little bit about what we actually mean when we talk about adding resistances. So resistance series, the total resistance adds together. And for resistance parallel, you have to use this equation. 1 over RT equals 1 over R1 plus 1 over R2. A bit irritating, but not too hard to actually use in practice. Worth noting that this simplifies if you've got two of the same resistors, both the resistance R, and you can try this yourself just to confirm if they're in parallel, then this thing simplifies to RT equals R2. So it should make sense that the total resistance has fallen because you've got two paths, each of resistance R. So in terms of using our analogy, it's easier for water to flow down overall than if there were just one resistor. So, and the general form for N resistors in parallel like this is RT, if they are all the same resistance, just as a quick shortcut to know, is R over N. So, but what I want to talk about here, because it's very simple to say, okay, well, that's how you add resistance. But what do we actually mean when we say, you know, add resistance? Well, what we're saying is that when we say we're adding resistances, we're asking what is the resistance of a single resistor that if we were to take out this big block and just replace it with one resistor, our circuit would be unchanged. So for example, if I've got N resistors in parallel like that, I could redraw that and say that's the same as just having one resistor of resistance R over N. Now, that's actually very important and very helpful because if you have a complex resistor setup, it can be quite hard to sort of get an idea of what's going on and what do they mean when they say total resistance, etc. Well, effectively, all you want to do is take it in steps and just simplify it by redrawing the resistors by replacing them with resistors of equivalent resistance. So if we take a look at this setup I've done here, well, what can we do? We can say, well, these guys, they must just be a resistance of 2 because they're in series. So we replaced them like that. These guys, you can also say they're resistance of 2. We've got that. And these guys are two resistors in parallel of equal resistance, so we can replace them with a resistor of a half. And already we've simplified this circuit quite considerably. Now, just sort of following this idea through, well, I could, just to make this clearer, I could say, well, these two are two resistors in series. So I can replace, well, I haven't actually done it there, but I could replace them, fine. But these two are two resistors in parallel, so I can, using 1 over RT equals 1 over 2 plus 1 over 1, flip it over, you get that they are a single resistor of 2/3. So I've done that. And now we've just got 3 resistors in series, so we can add them up and say, overall, this circuit is the same as if we had one resistor of resistance 19/6, which means the total resistance of the circuit will be 19/6. Now, why is that helpful? Well, what that will allow us to do, for example, is if we know the voltage of the battery, 10, then we can say that the current flowing in the circuit will be using V equals IR. We can say that I is equal to V over R, so 10 over 19 over 6. And when we say total current flowing in the circuit, what do we mean? Well, as you can probably imagine, the current is going to be splitting all over the place with this setup. So when we say total current, we actually just mean the current before it's split. So we've got, that is, what did I say, 60 over 19. So we know that we've got 60 over 19 there, very thick pen, and we've also got 60 over 19 current coming back in at the end. And obviously it's going to split at these points. Sort of all over the place, going to get nice and confusing, but we know that sort of the total current in the circuit is that, and that will be very helpful for more complicated questions down the line. Okay, that's sort of the introduction finished. Now we're getting on to the sort of important bits where questions are usually focused. And the first big thing is the idea of potential dividers, which is really just a fancy way of saying components in series. Obviously, it sounds like a very, the idea of potential dividers sounds complex, but literally, what does it mean? Well, it means dividing potential, or potential being another word for voltage. And as we've already seen, when does voltage have to get divided? Well, it's literally, since voltage is just the amount of energy spent by an electron, well, when does voltage get divided? Well, only if things are in series, because it has to choose, well, how much do I spend here and how much do I spend here? So that's really all a potential divider is. Now, obviously, there's practical applications, but that's the basic idea of a potential divider. So the obvious question is, and to be honest, the question that is the answer to the majority of electricity circuits questions at A-level is, how do we determine how much energy each component gets? So let's say in this circuit we've got here, we know that this battery has a voltage of V. And we've got a variable resistor here with resistance R1 and a resistor, a standard resistor with resistance R2. Well, each electron takes one path around the circuit, and we know by the time it gets here, it hasn't spent anything, so it's still got V left. By the time it gets here, it's got 0. So it must have spent some amount across R1 and some amount across R2. But how does it choose how much to spend? Well, if we say that we know that the components in series, the current from both of them is the same. And so using V equals IR, we can say that V1 equals I R1. Nice and simple. And V2 must be equal to I R2. And literally, just by dividing those equations one by another, we can eliminate I and get the potential divider equation. V1 equals V2 R1 over R2. Now, this is the most important equation you'll come across in electricity. It's a very simple equation, and it's actually extremely helpful and powerful because it does not involve current. And a lot of electricity questions, you will know the resistance of components, you will know the sort of voltages you're working with, but you won't know the current. Now, before I move on, let's just sort of stop and talk a bit about what I mean by that. Resistance, we've already said, is an intrinsic component, intrinsic property of the circuit. So resistance is sort of, for any given set of conditions, the resistance of the circuit is fixed. You aren't, by changing the amount of voltage, you aren't changing the resistance necessarily. Certain components are more complicated than that, but just for this purpose, you can get the idea that resistance is an intrinsic property. Voltage is fixed by the battery. Voltage being the amount of energy you're supplying, so I suppose V total is really what we're talking about. You're supplying a certain amount of energy to the circuit, so voltage is also fixed. And so knowing that I equals V over R, I current is the result of a supplied voltage and resistance. Now, why am I spending time on talking about this? What I mean is you will see often the idea of how do you do something in a circuit where you want to increase the current. But the current isn't actually something we have direct control over. All we have control over in a circuit is resistance and voltage. We can choose the resistance by varying what we put in there, and we can choose the voltage by choosing what battery we use. But current is the result of those choices because it's V over R. So if you were to say, okay, I want a circuit with a circuit of 10 amps, you wouldn't just be able to go and get a 10 amp circuit. You'd need to say, okay, how do I get a circuit with 10 amps? Well, of current. Well, I need to pick the right voltage and resistors to get that circuit to have 10 amps. So keep that sort of order of causation in mind when you're thinking about question. And hence, returning to our potential divider thing, V1 over V2 equals R1 over R2 is very useful because often current is not something we have particular control over or particular interest in. And so this is a very important equation. Now, using the fact that we know that the voltage of the battery must be equal to the voltage across R1 plus the voltage across R2. So we know that V1 plus V2 is equal to V, simply because, well, it should be obvious from the diagram, but the energy supplied by the battery must be spent across those two components. We get sort of a set of simultaneous equations we can solve to find V1 and V2. But to be honest, in electricity, especially at A level, you should find that you're able to sort of eyeball the voltages and the numbers involved much more often than not. And actually doing sort of complex maths is not usually that needed. You're much better off just sort of seeing what the actual answers are. So I'll give an example of this. But the key point is that for components in series, the ratio of the voltages is equal to the ratio of the resistances. Okay? So let's say we have this set up here. We know we have 12 volts in the circuit in general, and we've got 12 units of energy to spend across these two resistances. And we know that the share of energy that each one gets is the same, in the same ratio as the share of the resistances. So in this case, we don't need to do any sort of complicated simultaneous equations or anything, because we know this guy is twice the resistance of him, so it must get twice the energy. And so you can say that very quickly. You can see, okay, well, how do we share 8? How do you share 12 between two things where one gets twice the other? Well, it must just be 8 and 4. And so those will be the voltages across each of those components. Now, in slightly more complicated setups where you can't just sort of eyeball it, this is an alternative version of the potential divider equation that's actually much more useful, which is V1 over V total equals R1 over R total. So in other words, the proportion of energy that a component gets is the same thing as how much of the total resistance that component has. So if we see this sort of more complicated looking setup, well, just sort of following this through, okay, electron starts with 12 and finishes with 0. So by the time it gets here, we know it's still got 12 and it's still got 12 there. And it must have 0 here and 0 here. So each electron has sort of a choice. It can either go down this branch or down this branch. And it must spend 12 units of energy regardless of what branch it goes down. So this lower branch, well, it's nice and easy. We can sort of just see, okay, well, one of the resistors is double the other, so he must get 8 and he must get 4. But this top branch, you're not really going to be able to eyeball it that easily, so how much each one gets. So what you want to use is this simple equation. So you just ask yourself, well, what proportion of the total resistance does a resistor have? And that would be the same as the proportion of the total voltage it gets. So in other words, how much resistance does this branch have? Well, 7 plus 13 plus 1 plus 3. So we get 24 in this branch. And so across the entire branch, we know that there's 12 units of energy being spent. And then how much does each resistor get? Well, it's just how the share of that is however much of the resistance the branch has. So this first one, for example, it's got a resistance of 3. And we know the total resistance is 24. So it gets an 8. 1.5 volts. And you can see I can sort of do the same thing. all the way down, and we get an idea of how many volts each component gets. And notice how I've labeled on at each point as well how much energy we've got left for each electron. Now, it's not necessary for every question, but it's just it's very useful to do, and will be very helpful for most questions. So that's covered potential dividers, sort of how to do the maths behind them in an easy way. But let's sort of talk about quickly why they're useful. Well, if you imagine most components that you know in your house, they require a certain amount of voltage in order to function correctly. If they have too little, they won't run, and if they have way too much, then they'll probably break. But the mains is it's alternating current, but for the purpose of this guide, let's just imagine it was direct current. Mains is that voltage of 230 volts. And so if we had no choice but to connect to components at 230, well, we'd just end up breaking everything. And so what does a potential divider do? Well, and imagine you have sort of a set of batteries that are all a certain number of volts, and you want, you've only got 10-volt batteries and you want 1 volt for your component. Well, if we use a potential divider setup and sort of connect the component across here, which would be the output potential difference, e.g., because we can say that, well, in this circuit, let's sort of talk about it the other way around. So if it starts off with, well, let's say it's got, well, the voltage across R1, E1, will simply be equal to the total voltage supplied times the share of the resistance it has. So R1 over R total, which is R1 plus RV. And so just to make this clearer, we could also divide both top and bottom by R1, and we get V over 1 plus RV. Okay. And so what we can say is that by varying RV, we can make this anything we like. And if you imagine sort of increasing RV towards infinity, then we could make the voltage effectively 0, or if we decrease it towards 0, we can make the voltage V. So the most important thing about potential dividers is that we can get to any output voltage we want in a very easy way. So that's the most important thing. And just quickly addressing, why is this the output PD? Well, very simply, if an electron has, well, we know that electron here must have energy 0 because it's almost finished. It's that. So it's got 0 there. And we know that it's spent V1 across here, so it must have V1 units of energy there. And therefore, any electron at that point, that path, can either choose to go down through here and spend V1, or it could go along here. And we know that, and then sort of, do its thing and come back. And we know when it comes back, it's got 0 units of energy. And when it started off, it had V1 units of energy, and hence sort of this whole sort of sub-circuit must have a voltage of V1, which is why we can say the output PD is V1. So that's sort of potential dividers, and just notice how simple it is. And the most important thing is that you don't have to look at current. And so in a lot of circuit questions, just if you find yourself not sure what to do, or just see what they've given you. If they've given you V and R, just ask yourself whether you even need to bother finding current, or whether potential divider setups would be sort of a much quicker and simpler way of dealing with it. So we'll look at a few questions involving that in a second. But first, I just want to mention the most important thing about potential divider setups is that the share of voltage a resistor gets depends on the total proportion of the resistance that the circuit possesses, not the absolute value of the resistance. And this is another reason why potential divider setups are useful for answering questions rather than thinking about current. Because what you can do is decrease the total resistance of or increase the total resistance of the circuit, but the voltage across the component we're talking about decreases, or the other way around. So, for example, here, you can say that what we've done is we start off with a circuit like this, and a question might be, okay, what happens to the voltage across here if we increase the resistance? Well, in this component, well, in this diagram, what we've done, we've increased the resistance of the component, but the voltage has gone down because we've also increased this other resistance. Whereas in this diagram, we've increased the voltage, the resistance of this guy, and it's increased the voltage. So the point being that you want to remember that the resultant voltage is always dependent on a ratio, the ratio of the resistance to the total resistance, not just on the resistance of the object itself. So the last thing to mention with potential dividers is just when you see things like this, sliding contacts, effectively all you're doing is dividing this long thing into two resistors, depending on how far along you are. So if you're a quarter of the way along, as you can see, it sort of splits into quarter and three-quarter resistors like that. So let's just, before we move on, let's quickly just illustrate how this can be used in sort of a practical sense in questions. So let's say we have this set up, very common. We've got a bulb here, and a bulb here. And they want to know what happens if this guy breaks the other two bulbs, the brightness of the other two bulbs. Well, as we'll talk about later, brightness depends on power, which we can say is V squared over R. We'll talk about that later, but for now, let's just sort of stick with that. So what often people want to do is they want to get current involved. And I personally recommend that if you can avoid it, try just not introduce current and just work with voltages and do that via the potential divider. So initially, what have we got? Well, battery is voltage V, and if each lamp is resistance R, what can we say? Well, we can say this whole little block is resistance R over 2 using the parallel setup, and this guy's resistance R. And so using the potential divider idea, how much voltage does each one get? Well, this guy gets twice as much as these guys, so this guy must get 2V over 3, and this guy must get V over 3 because the voltage is shared in the ratio of the resistors. And so just labeling on what we mean by that, well, we've got V units of energy here, we've still got V here, we must have 2V over 3 left after that, and 0 left there. And at this point, the electron sort of goes in and chooses what path it wants to go down, but it doesn't really matter which path it goes down because it's going to have spent V over 3 on this guy and V over 3 on this guy. So that's set up there. But then if we break one of the bulbs, what happens? Well, we've now effectively just got this circuit. One of the bulbs is broken there. So now we've got this new circuit, and now this guy's R, this guy's R. So now they both must get V over 2. And using the idea that power is V squared over R, we can see that in the original circuit, let's call this guy A and this guy B. We can say that power of A was, well, it's V squared, so that's V squared over 9, because it had V over 3, over R. What's the resistance of A? Well, we're just talking about this single bulb A, and so he must have resistance R. Oh, what's happened there? Okay, we're back. And so that's just over R. So his power must be V squared over 9R, and PV must be 4V squared over 9 over R. So 4V squared over 9R. Okay. Now, so that's sort of the first setup, and then the second setup. Well, just looking at it, both PA equals PV equals V squared over 4R. I believe just sort of cutting V squared over R. And so what's happened? Well, PA, so in other words, lamp A has gotten brighter and B has gotten dimmer. And notice how, personally, I think that was relatively easy, and we didn't have to introduce the idea of current or anything like that. All we had to do was look at the voltages and how those change using potential dividers. So you can see it's a very useful tool to avoid confusing sort of current calculations. Now, if you can't avoid using current, which occasionally is tested, what you can say is that current divides in a very similar way to voltage. So in series, voltage is shared, so that's the potential divider, and current is not split. And in parallel, voltage is not shared and current is split. So what we can say, just using our intuition, we know that in parallel, well, using the idea of electrons, each electron has to make a choice. So voltage won't split because each electron has to spend all of its energy, regardless of what path it goes down. Whereas current obviously will split because some electrons choose to go through the top path and some through the bottom path. And so you can sort of see here, I've just got more potential divider things going on. But oh, and here we've got a question using potential divider setups that was multiple choice with 4 answers, and the correct answer was given 22% of the time. In other words, worse than random. So it's very clear that voltage is an area of difficulty for a lot of students. But you can see that if you use this method, it's actually sort of extremely easy because you just sort of label on how much energy each electron has at each point, and the reading on the voltmeter will just be the difference. So in other words, 4. That should make a lot of sense to you now. So before we, have I skipped the, okay, so before we actually talk about the current divider, let's talk about how you can avoid doing sort of complicated current calculations and sort of take shortcuts in some questions. So if you have components in parallel where each loop does not share any components other than the parallel, so the power supply, this is very important. Only use this method in this situation. It can make questions extremely easy and intuitive, but it does not work if they share other components. So in this case, for example, in this setup below, you can see that we can sort of draw 3 loops and none of which share any components other than the power supply. In this situation, each loop is completely unaffected by changes in other loops. So basically, you can just say the whole circuit is just all 3 of those loops added together. So if you wanted to work out the total current in the circuit, you can just work out the current in each of the loops and sort of add them all together, like that. So that's just one thing worth knowing. And it also can be helpful for questions involving bulbs, for example. Let's say I've got a setup like this. And they want to know what happens to this bulb if this bulb breaks. Well, the answer is nothing because they're in completely separate loops. And so changes in one loop doesn't change anything in the other. But just be very aware and do remember that the moment I add a bulb up here that's in both of the loops, I can no longer make those claims, and changes in one loop will change the others. So just remember that. And that's sort of what we're talking about there. Okay, now just illustrating, just remember the idea that you cannot have different energy of electrons at a single point. So if somehow, in some setup, you know for sure that an electron went in here at 10 units of energy, and you know somehow that it's got 5 units of energy left here. So let's say we didn't actually know the resistance of this, but we know that it's got a voltage of 5 across it. Well, then what can you say for sure? Well, you know for sure that there is a voltage of 5 across this bottom one as well, simply because we cannot have a different answer here to what we have here, because obviously if an electron has 5 units of energy here, then it will also have the same amount there because it hasn't spent any more. And so they have to, just using this, just remember that for things in parallel, they'll have the same voltage across them, simply because the electrons start off with the same amount of energy and finish with the same amount of energy. So they have to have the same voltage across each. So for example, regardless of the setup, whatever this component is, this component. What can I say about them? Well, I can say if that's got a voltage of V across it, then let's just make sure we see that. Then this must have a voltage of V across it. Okay, and that simply results from the fact that there's a certain amount of energy here. The electron can choose either path, and we know by the time they get here, they must have the same energy left. So the voltages will be the same. But that introduces some important ramifications, because what we can say is that the voltages for each path will be the same, but the resistances can definitely be different. Like choosing different components can make the resistances different. And so because of V equals IR, we must be able to have different currents flowing in each path, because otherwise just the maths wouldn't add up. And using a very similar setup to potential dividers, for each path, we have that the voltage is the same. And so we can say that V is equal to I1 R1, but the same V is also equal to I2 R2. If, for example, just explaining what I mean here. If we get resistor there of R1, resistor there of R2, current there of I1, current there of I2, and we know across both of them, we've got V. So V is equal to I1 R1, and V is also equal to I2 R2. And if you equate those, you get I1 R1 equals I2 R2, or more usefully, the current divider equation. I1 over I2 equals R2 over R1. So very similar to the potential divider setup, but just notice that it's actually the other way around. It's that the current is shared in the ratio of resistances, but in the opposite way you might expect. In other words, the smaller resistance path gets the larger current. Now that should make sense, because smaller resistance path is like a bigger pipe. So just remember that. And so again, especially in A level, you will not have to do any very complex current calculations. You usually don't have to do many current calculations at all. You can usually get by with potential dividers. But if you do find yourself having to work out the current in a path, it can be useful to know that, let's say you know let's say we want to find the ammeter reading here. Very nasty question. So how can we do that? Well, the first thing we want to know is what's the total current in the circuit. So in order to do that, we have to just work out the total resistance of this circuit, because we can't use the loop method because the loops share components. So if we find the total resistance in the circuit by adding up all the resistors in that way, we find that the total resistance is 7 ohms. And the total current will therefore be 12V over R, which is 12 over 7. Okay, that's the total current. And so then what we can say is, well, we've got 12 over 7 to share, and we know that the current splits here. And how does it split? Well, it splits according to the ratio of the resistances, the parts. Well, in other words, so one of them is 3 and one of them 6. So the top guy, because he's the smaller resistance, he's going to get 2/3 of the current, and this guy's going to get 1/3. So it's very similar to potential divider and sort of eyeballing it, but just make sure you remember that the smaller current, the smaller resistance path is the one that gets more. So obviously you can see it's going to split in a 2-to-1 ratio, but just the 3 is the one that gets double the current. And therefore you can sort of see we worked out what the currents in each path is. There are lots of different ways of working out current. I'm just showing the potential divider method, the current divider method here, because it's not really mentioned sufficiently in A level, but it can be useful. An alternative way that you can work out current in certain paths is if you know the voltage that's used across that path and the resistance, then we can use I equals V over R. So actually, let's do that on this question. So we have, how are we going to work out the voltage across a path? Well, we're just going to use potential divider. So in other words, we've already worked out the total resistance of the circuit. That's 7. And what can we say? Well, we can say that this block here has a total resistance of 2. If we do 1/3 plus 1/6, 1 over that, we end up getting 2 ohms. And so how much voltage does that path get, that little block, we know that the voltage is equal to 2 over 7 times 12, which is 24 over 7. So that's how much voltage is across this path. In other words, just make that clear. This guy gets 24 over 7 volts. And this guy also gets 24 over 7 volts. And now we can just use V over R to find I. So I1 is equal to 24 over 7 times 3, which is 8 over 7, which is the same answer if you got using the current divider method. So lots of different ways of doing it. Use whichever one you're more comfortable with. Okay. Now moving on to sort of the later parts. These earlier parts were sort of the more foundational methods. They actually, to be honest, build everything you need for the later parts, but it's worth going through these later things just so you don't have to work it out yourself from first principles. So a lot of the things in this later section will be sort of the tricks they like to ask. And again, like the earlier part, it will be sort of very even more examination question focused. So one thing is that cells in series behave very much like resistors. You just add together the voltages. But one thing that they occasionally do is if you've got a battery going the wrong way around, so we've got 6 volts, 6 volts, and 6 volts, but you notice that this guy's the wrong way around. So if you imagine an electron going through, he's going to get +6 here, but then he has to sort of fight through this battery. And when it fights through, it ends up losing 6 units of energy. And then it fights through, it gets through and gets to here, and it gets another +6. So in other words, the total voltage of this setup would just be 6 volts because one of them is the wrong way around. So just be aware, if the battery is the wrong way around, it means that you lose energy, you don't gain it. Cells in parallel, however, these are slightly more tricky. And keeping in mind that you're always talking about electrons flowing around circuits for voltage. So if we have an electron coming in here, and it must be at 0 energy because it's spent it all, well then it's got a choice. It can either go up here and get 6 units of energy and finish at 6 here, or it could go down here and get 6 units of energy and finish at 6 here. But it can't go through both. And so if you've got cells in parallel, you actually only get the voltage of one cell. So that might make you think, okay, well, why would we ever put cells in parallel? Well, there is a reason, and we'll talk about that in a bit. But just remember that no matter how many cells I have in parallel, just keep in mind how many, that's very bad drawing, you get the idea. Just ask yourself, well, if I'm an electron, what's the best I can do? How many cells can I flow through? And that will give you the voltage. So if these are all 6-volt batteries, well, an electron comes in here, what's the voltage of this setup going to be? Well, if I'm an electron, I'm going to choose, the best I can do is choose to go down here, because then I get to go through 2 of them. And so this setup would have a voltage of 12 volts. Okay. Electrical power. The definition is P equals IV, and also you know that P equals energy over time. So the electrical work done per second is equal to the product of the current and the voltage through a component. Now, this is a useful form of power, but only if you know both the voltage and the current. Usually, we're given the resistance, and even more commonly, we're almost always given the resistance, and we also usually have an idea of the voltage. It's actually the most rare for us to know the current. So you can sub in V equals IR to that power equation and get these alternative forms. P equals I squared R and P equals V squared over R. And effectively, you want to use the one in the question based on what they have given you. If they have given you V and R, then just use this. There is no reason to work out current. And if they've given you I and R, then there's no reason to work out voltage. Just use this one. V squared over R tends to be the most commonly useful one, simply because you very often have the voltage and the resistance. And if you have the voltage and the resistance, just make sure you do not use P equals IV, because effectively, for example, if I double the voltage, then it can be very tempting to say, oh, well, if I double the voltage of a component, then the power, since P was IV, if I double V, then that must go to 2P, right? No, because when you change the voltage, remember that the current might change as well. But when you change the voltage, the resistance is unlikely to change because it's just an intrinsic property. So actually, P equals V squared over R is much more useful, because there you can see that if we double P, that goes to 4 times the power, because we know the resistance is unlikely to change. Similarly, if you've got the current, you're much better off using I squared R, because again, if the current's changing, that suggests the voltage is changing, but it doesn't likely suggest the resistance is changing. So just make sure you use the correct form of power based on what they've given you in the question. And in general, unless they've given you both the power, both the voltage and the current, you're usually better off sticking to these options rather than P equals IV, simply because you have to consider what happens to I when you change V with this one. Okay, one quick distinction to be made. With power, there are two things to think about. Some components, you've got the power required to make a component function properly, and you've also got a certain power at which point above that, the component will break. Now, if a lamp is considered a 30-watt lamp, then that does not mean always uses 30 watts. What a 30-watt lamp means is it means that the lamp is if it's being used correctly, it's using 30 watts. So if they tell you in a question that the lamp is at normal brightness, you know that it's got 30 watts going through. Otherwise, you can't assume it's using 30 watts. All 30 watts tells us is that that's how much it's supposed to be using to work properly. A fuse doesn't have a power requirement. So if they talk about a fuse that's rated at a certain level, what they're actually talking about is that above a certain power, it will break, or current or voltage, depending on the fuse. That's the point of a fuse. It breaks if there's too much energy in the circuit to protect other components. Similarly, a resistor doesn't have a power requirement. It will work regardless of how low the power is, but it may break if the power is too high. So just in power questions, just make sure you know whether you're talking about the power required, e.g., so if it's power required, you want power supplied to be greater than or equal to power required. But if it's power breaks, well, then you want that to be greater than or equal to the power supplied. So it does matter, and it's just important to just be aware that, you know, there can be a difference in terms of what you're talking about when you talk about power. Electrical efficiency, very easy. Electrical power is IV. If the circuit is being used by mechanical power, e.g. heat or lifting something up, if it's only 30% efficient, then you can sort of it's worth writing down that the actual power that you're getting out of it, the useful power, is just the efficiency times the actual power being supplied. Okay, now a list of electrical components. I'm not going to go through them. We've gone through some of them already, and I'm not going to go through them in huge amounts of detail, except for the most important ones. So ammeter, we've talked about. Voltmeter, we've talked about. Cell, we'll talk about further in a bit. Bulb, we've talked about. We'll talk about it in a bit more detail. Just remember, bulbs do not obey Ohm's law, which again, we'll talk about in a second. Diodes, we'll talk about in detail in a second. Light emitting diode is just a diode that tells you when it's working. Resistor, so a fixed resistor, it's a constant resistance and it obeys Ohm's law. Ohm's law is that voltage is directly proportional to current. You need to remember this. In other words, V equals IR. And so on a IV graph, if something obeys Ohm's law, well, rearranging this, I equals V 1 over R times V. On an IV graph, if voltage is directly proportional to current, then we know that it's going to be a straight line through the origin. And the gradient, as you can see there, is 1 over R. So on an IV graph, if something is a straight line through the origin, it obeys Ohm's law. And just remember this, Ohm's law is voltage is directly proportional to current. And resistors dissipate power as heat. That's I squared R, or whatever. That's the heat that will be dissipated. A variable resistor is an ohmic resistor. It obeys Ohm's law, The only difference is that it's like having lots of different resistors. You can choose what resistance it has. And so when you're not touching a variable resistor, it's a fixed resistance, like when you don't adjust it. So it must obey Ohm's law. It's just that you can change what resistance value it takes. So you can make it steeper or less steep, but they're all going to be straight lines through the origin. When do you use them? Almost all the time in potential divider setups. And effectively, these are probably the most, you almost any circuit you draw, especially for experiments, you're going to want a variable resistor in, because it allows you to get different V and I readings, which is usually what you want for an experiment. So just remember in your experimental circuit setups to just include a variable resistance so that you can vary the resistance and get different V and I results. And that's usually, you then usually plot a graph and get the results from that. So they're very useful and they come up all the time. Okay. Thermistor is a resistor that, again, just remember, these are trick questions almost. Thermistors do obey Ohm's law. The only difference between a thermistor and a normal resistor is that it changes resistance as the temperature varies. So at a given temperature, it is a straight line through the origin because it obeys Ohm's law. And depending on the type, usually you'll have a negative temperature coefficient. But basically the temperature coefficient is just whether or not, if it's a positive temperature coefficient, resistance increases as the temperature increases. Negative means resistance decreases as temperature increases. In general, resistance usually decreases as temperature increases for thermistors. But so just remember that they do obey Ohm's law. The gradient on an IV graph is 1 over R. And so at a high temperature, well, high temp for a thermistor implies low R, which implies 1 over R big, right? Just sort of think that through. In other words, at a high temperature, you'll get a steep line on an IV graph, and a low temperature, you'll get a shallow line. Light-dependent resistor, very similar to thermistors. Again, they do obey Ohm's law at a given level of light. Just remember that the resistance decreases as light increases. A heater is effectively just a resistor, dissipates power as heat. A motor converts electrical power into mechanical power, obvious. Okay, so now that those are all the sort of components that we really care about. Let's talk a bit more in detail about some of them. So first of all, bulbs. They love this question for 3 or 4 marks. So the first thing I'm going to mention is just pay very close attention to whether or not it's an IV graph or a VI graph. It really doesn't make much of a difference, but if you think of the fact that I is equal to V over R, or in other words, 1 over R times V, it's an IV graph. Well, I is the y-axis and V is the x-axis. So the gradient, M, is 1 over R. Now, usually it's an IV graph, but occasionally it might be a VI graph, in which case V is equal to R times I. And so if V is on the y-axis, then the gradient will be equal to R, not 1 over R. So just pay close attention to that. But assuming it is an IV graph, well, as you can see, a lamp is not an ohmic resistor because it's not a straight line. And let's talk about, well, this is the shape you need to know, this sort of shape we've got here. But let's talk about what's going on here with the resistance and figure out if we can understand why. So here we've got steep, not steep. And shallow. So what we actually said here, we said high I implies shallow, positive or negative. What does shallow mean? Well, it means 1 over R low, which means R high, and low I, so the opposite is R low, right? It's steep. So why does it have, this is a very important graph to know, and they love this 3 or 4 mark questions. So why does it take that shape? Well, at low currents, the temperature is low, and so it's got a low resistance. But as you increase the current through a lamp, the filament heats up, and what that tends to do is it makes sort of the atoms inside vibrate more, and more electrons, sort of more things getting in the way of electrons trying to go through. And so as the filament heats up, the resistance increases because of the sort of more difficult, because it's more difficult for electrons to get through, and so it becomes more shallow. So make sure you remember that and know it off by heart for questions. Okay, now we've got an entire sort of small section on diodes, simply because they are very important and very poorly understood. So the analogy I'm going to use for diodes is just think of them as you are, when you're going on a circuit, you are trying to travel around the circuit. You're sort of making your way along, all happy. And a diode is a gate with a little tax or a toll. You are only allowed to go through the gate one way. So if you try and go around this way, you're not allowed. So that's the main thing the diode does. But the other thing is, if you do want to go through the gate in the correct direction, then they will let you, but only if you can pay the toll. And the toll is usually about, they take the tax in volts, or in other words, an energy toll, and it's usually about 0.6. But just remember that in order to travel on the road, you're going to have to pay that toll. And it doesn't matter where the diode is. Let's say we've got this nice circuit, you know, there's some resistors here, bulb here, another resistor, and then at the end of the lap, I've got a diode. And just basically just think, the way to think of it is just remember that electrons are not going to start off down the road. And let's say we've got 10 volts here. Electrons are not going to start off down the road unless they can pay the toll. So if, let's say we've got a very low voltage battery, we've got 0.3. Well, what's going to happen? Well, the electrons aren't going to be allowed to travel along the road. And unfortunately, the diode is going to take all of their money. So that's the voltage through them, through the diode, which leaves nothing for the rest of them. Whereas, assuming you have got enough energy, then regardless of where the diode is, even though it's at the end here, he's still going to take his toll of 0.6 volts or thereabouts. It depends on the question, they'll tell you. And so what can we say about that? Well, we know that we've got 0 left here. We know we've got 0.6 here. We have to save our 0.6 to pay the diode gatekeeper. And we know we start off with 10. And so in order to do this circuit calculation, what we can say is that, well, however, what it's done is it's spent 9.4 volts on the rest of the components. And so in order to do calculations involving diodes, you don't want to use the voltage of the battery. You want to subtract the toll that the diode has taken, and then you can use the volts that are being spent across the rest of the components to do all your calculations. So, you know, you can work out the current or the voltage, etc. So that's just something very important to understand about diodes. You won't be asked to calculate the resistance of a diode. It's infinity in the wrong direction, and also infinity below 0.6 volts. Above that point, their resistance sort of profile becomes very complex, and you won't be asked about that. And also, you don't need to worry about it because you know they're just going to take this. They're just going to take this toll of about 0.6. And so, looking at that on an IV graph, this should make sense. They're not allowing current through the wrong direction. They're still not allowing current through until you've got the right amount of money, at which point they just say, yeah, go on ahead. We're not going to charge you more than this amount of voltage. But just be aware, the resistance is not 0 above 0.6 volts. So it's the line becomes very steep, but you can see it's not vertical. So the resistance isn't 0 above 0.6 volts, and you never have to calculate the resistance of a diode when it's being used correctly. You just need to know that it's infinite if you're not trying to use it correctly. So just notice how diodes are very different to other components. Usually when we work out voltage, we say that, oh, they get a certain proportion depending on the resistance, blah, 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 blah. Whereas diodes, you just know, okay, they're little gates and they take a toll and they're very happy. Once they've got there to 0.6, they just said, yep, that's enough for me, and spend the rest amongst the other components. So let's just do a very simple question using a diode. Let's say we've got 1.5 volt battery, a resistor of 10 ohms, a diode that uses up 0.6. So, and we want to work out the current. So just labeling this on, we know that this guy's taking 0.6 volts. And so that leaves 0.9 for this guy, because that's the only other place for electrons to spend it. And well, what can we say about that? Well, if V equals 0.9 and the resistance of that component is 10, we say that the current across this resistor must be V over R, so 0.09 amps. And since that's the current across the resistor, well, we know that's the current in the circuit in general. And so that's how you deal with diodes. Notice how I didn't use the very common mistake is to do I equals 1.5 over 10, but you're not allowed to do that because some of the voltage has already been used by the diode. Okay, we are slowly getting there. So now we need to talk about EMF and internal resistance. So the first thing I'm going to say is that just be aware that physicists don't stick to these exact rules and quite flippant about what they call voltage or EMF. I'm sure I have been in this video, but just know the definitions, which is an EMF, which stands for electromotive force. It's not a force and it has units of volts. Very bad name, very annoying, but just remember that EMF is a voltage and it is defined as the energy supplied to electrons by a power source. And so, for example, a 12-volt battery always has an EMF of 12 units because it gives electrons 12 units of energy. Voltage tends to refer to energy used up by components. So EMF is sort of energy given, voltage is usually energy taken away. They don't tend to stick to this very well, so don't get confused if they're not, being exact about these, but just that's really what's actually going on. So up till now, we've considered ideal batteries, e.g. ones without any internal resistance. And now we're going to introduce the idea of internal resistance in batteries because it's more realistic. Effectively, with our assumptions, if I'd set up a circuit like this with a voltage V, well, according to what we've done, we said there's no resistance in this circuit. And so, the current is going to be infinite. Now, in practice, that's obviously not going to happen. And so we need to sort of have an explanation as to why. Well, you might say that you might argue, well, there's a resistance in the wire, but actually, fine, I can say, well, what if I give you a wire made out of a superconductor? So there's no resistance in the wire. Will there then be an infinite current? And the answer is no, because all batteries are not 100% perfect. They actually have a small resistance themselves, which we usually give it the little letter R. And so no circuit you create will you be able to get zero resistance in total. And that shouldn't be surprising because zero resistance leads to the idea of infinite currents, which just is a bit silly. That's arguing infinite. It's remembering that current is the amount of electrons flowing. Infinite current means infinite electrons flowing every second, which is just, obviously impossible. So that's very simple, the idea of what internal resistance is. And actually, technically, that's it. Like, you could do questions involving internal resistance without any further knowledge because you just add a little resistor there and then do the question as normal. But it's worth sort of looking at what we do with internal resistance just so you don't have to do it from scratch. So let's say a battery has an EMF of 12 volts. Well, are we actually that interested in how many units of energy a battery gives the electrons? Not really. What we're interested in, if we have a little component in the circuit that we're trying to power, then what do we care about? Well, we care about how much energy this component gets. And how much energy does that component get? Well, the answer is not actually 12 volts, because no matter what we do, this guy is going to steal some of our energy, some of the energy for the electrons. And so what we say is that this voltage V across here, we'll call that VT, which is the terminal voltage, e.g. that would be the same as if we measured it up here, right? Because if that's VT and that's 0, then this is VT 0. So they're the same thing. So we call the voltage we're actually interested in the terminal voltage. In other words, the voltage supplied to the rest of the circuit that isn't used up by the battery. And so once we've done that, we can sort of do some very simple algebra to sort of have a look at what that does. So we can say that the energy used must be equal to the energy given to each electron. The energy given is just the EMF of the battery, E. And the energy used is the voltage across the internal resistance, VR, and the voltage across the rest of the circuit, the terminal voltage, V-term. So this equation is just conservation of energy. And then the sort of very common and useful form of this since E is just a constant, we can rearrange this and get that V terminal equals E minus voltage across the internal resistance. But we know the internal resistance is just IR. The voltage across the internal resistance is just IR. So we get this very, very important equation. Very simply, where Vter, just remember, it's as far as you're concerned, it's the voltage you've always been measuring in experiments. You can't really get a measure of the EMF very easily. It's not relevant to most questions because you're measuring the voltage that gets to the circuit. In other words, the terminal voltage. And so Vter, well, this is a constant. And so is this R. And so in other words, just looking at that, the amount of voltage that gets the circuit depends on the current. As the current goes up, the internal resistance will use up more and more of the EMF of the battery. And so if we plot a straight line graph, which you will get so many 3-mark questions on this, so make sure you understand it. It's very easy if you are used to it. But in other words, you vary the I using a variable resistor. So you use a variable resistor in an experiment, you get a bunch of readings for voltage and current. And if you plot them on a graph, you get something like this. And if we put a straight line through them, then you should be able to see that, well, the y-intercept should be E. Just looking at this, when the current is 0, look at this graph, it's clearly a straight line. And the gradient equals minus R. And so, in other words, if you plot a graph that allows you to work out what the internal resistance is and what the EMF of the battery is. Now, there's a quick shortcut to find the EMF of a battery. Again, very important. They ask questions on this all the time. If I connect a voltmeter like this to a battery, now let's just draw on the internal resistance so it's correct. That's internal resistance, so it's about as simple a circuit as we could get. And if I just do this, now I know I said earlier you would never do this. You would never do this usually, but what have we done here? We've set up a circuit here with a resistance of infinity. And what's this voltmeter reading? Well, it's reading how much, because the voltmeter has resistance of infinity, and how much energy do we have here compared to how much energy we have here. So this is just reading the sort of voltage across the battery, right? There's nothing, if we have a resistance from infinity, but there's nothing flowing in the circuit. So we usually wouldn't bother doing this with a voltmeter because it kind of ruins everything if we have 0 current flowing. But it's still a circuit. And so what have we got in this case? Well, we are measuring the voltage across the terminals of the battery. That's clear, right? You sort of agree with that. And so what have we got in this case? Well, Vter is equal to E minus 0, because the current is 0, times R. In other words, just E. So what is the only situation in which we connect a voltmeter directly across a battery in series? Well, we only ever do it to get what the EMF of the battery is. Simply because if we connect a voltmeter in series with a battery like this, then the current drops to 0, and so no voltage is used up by the internal resistance. And so the reading on the voltmeter will tell us the EMF of the battery. So that's important. That's a 1 or 2 mark question that is often asked, and it's just 3 marks if you know what to do. Okay, that should all hopefully make sense. Now, you don't need to know, this maths may look a bit complicated here, and you don't really need to know the intricacies of the maths here, but the fact that voltage loss due to internal resistance increases as current increases does introduce a significant problem. When you're using circuits, you want to deliver what we're usually interested in is voltage, or more commonly power. And so you might say, well, okay, we lose voltage as we increase the current, so why don't we just use very low currents? Well, then, since power is IV, if you use a very low current, you're kind of stuck with a very low power. But as we increase I, then we're going to decrease V terminal more and more. And so at a certain point, we might also have a low total power, even if we've got high I, because the terminal voltage has dropped so much, all the power is being used up by the internal resistance. And so in order to maximize the power delivered to a circuit, basically what you want to do is you want to find a happy medium between current and voltage, and sort of, you don't need to know the maths behind this, but it's useful to know the understanding of the fact that there's this conflict. You want to deliver higher power to the circuit, but the higher current you use, the lower the voltage goes, and so it's sort of these trade-offs. So that's just the general thing you want to understand. Now, given that problem, you might sort of start asking, okay, well, how can we actually increase the power delivered without this trade-off? Well, we've got two ways. We can increase the voltage, or we can decrease the internal resistance, because that way the voltage will go down by less as the current increases. So this brings up, again, quite a common 4 marker, the idea of arranging power sources in series and in parallel. So it's very obvious why you would connect power sources in series. Well, that increases the voltage, right? So that's apparent from day one. But if you think about it, now we've introduced these idea of little internal resistors. What's happening as we attach more and more power sources in series? Well, we're increasing the internal resistance. And so even though attaching power sources in parallel, as we saw earlier, doesn't increase the voltage, what is it going to do? Well, we've now got resistors in parallel, and what do resistors in parallel do? Well, they decrease the total resistance. And so by arranging power sources both in series and in parallel, you can make stronger and more efficient batteries. The way to think of it is potentially that in series you get stronger batteries, and in parallel you're sort of increasing the efficiency by decreasing the internal resistance, but you're not making the battery any more powerful. So let's say we have a series of 10-volt batteries with an internal resistance of 5 volts each, and we need a power source with 100 volts and internal resistance of 10 ohms. How can we do that? Well, the first thing to look at is we need to get to 100 volts. How are we going to do that? Well, there's only one way. We put 10 batteries in parallel, in series. And so if we do that, we've got 10 batteries in a row, and that will give us a single power source of 100 volts, but internal resistance 50 ohms. So we then need the same voltage, but internal resistance 10 ohms. And so how can we do that? Well, the only way we can do that is by adding more of them in parallel. And so if we add 4 more rows of batteries, that will decrease the internal resistance by a factor of 5. And so we'll get to a power source of 100 volts with a resistance of 10 ohms. But obviously that's taken 50 batteries. So it's just worth being aware that that might be why you would see things in parallel as well as in series. Okay. And that brings us to the end of sort of the direct current electricity guide. Hopefully that was helpful. I think that if I just quickly do a couple of questions on internal resistance before finishing off, then you can have a look if you want to see more examples. There's more electricity videos on this YouTube channel that you can take a look at. But hopefully that's cleared up any problems you might have with electricity. So before moving on, let's just do one or more questions on internal resistance. So let's say we have a setup like this. And I am told that when I connect a voltmeter across the battery terminals directly, and separately, in this setup, I've got a reading of 0.0 6.4 volts. Okay, and the diode works at 0.6 volts. What is R? Okay, so this would be sort of a 3 or 4 mark question. And with electricity questions, if you've fully understood everything in this guide, these should then become quite simple. It's just a matter of labeling things on and sort of understanding what the information they told you. So the first thing is when they connect a voltmeter across the battery terminals directly, the reading is 9 volts. So as we said earlier, that must mean that the EMF of the battery is just 9. Okay, and then marking on this diagram with how we know things work, well, we know that a diode at 0.6 volts means that this guy is using up 0.6, and that's all he's going to use up. If this battery is 9, as an EMF of 9, we put 9 there, we know we've got 6.4 here, 0.6 volts there, and so we must have 2 volts across the internal resistance, because where else could they be going? And then just having a look at this, what else can we work out from this diagram? Well, just looking here, we've got a resistance and we've got a voltage, so we can work out current. So I is going to be 0.64 amps. Okay, and now that we've done that, we've now got everything we need, because we can say, well, across the internal resistor, we've got that B equals IR, and so 2 is equal to 0.64 times R, and so the internal resistance is just going to be 2 over 0.64, which is something like 3 point, I don't know, 3.2, who knows. The point being that, as you can see, the electricity questions are actually quite simple mathematically once you know what you're doing. You just want to really get good at labeling on all the different things going on and really understanding sort of how it is I did all this. So sort of, you know, the fact, just get very used to the fact that, well, that's 0.6, that's 6.4, so we know we've got 2 left. And then just noticing that there's a voltmeter, a voltage, and they've given us the resistance for some reason. So we should probably work out what we can from that, which is a current. And then once we've got that, we've got the current and we've got the voltage, so we can work out the internal resistance. Okay, so that combined with the YouTube video showing other examples should hopefully be enough, and hopefully that was helpful.